Good morning, everyone, and welcome to our today's webinar from the Quanser user series. We have invited Dr. Petar Durdevic from Aalborg University's Department of Energy Technology to talk about the research in his lab. My name is Zuzana Fabushova, and together with my colleague Murtaza Bora, we will be your hosts and webinar moderators today.
Hello, everyone. My name is Murtaza Bora. I'm a systems and control engineer at Quanser. I visited Esbjerg in October of 2018, which is the first time I met Dr. Petar at the Aalborg University branch in Esbjerg. He is an assistant professor at the Department of Energy Technology, Aalborg University, Denmark. His research is focused on modeling, control, and instrumentation, working with different offshore oil and gas, as well as water waste treatment industries. Petar is also part of the robotics team, developing drone systems for inspection and maintenance purposes. So without further delay, I'll pass it off to Dr. Petar.
So welcome, everybody. As Murtaza nicely introduced me, my name is Peter, what people call me in English, but really, my real name is Petar Durdevic. Originally, I'm from what was once called Yugoslavia, but I will come to introduction shortly. So I've been invited today, and I'm very glad to be invited to speak about some of our research at the Aalborg University Esbjerg campus. We have now had the pleasure to work with the Quanser and use the Quanser system for a little bit more than a year, and I will try and then explain our kind of experience with the system and how it has helped us with both teaching and some of our research. The title of the speech today is Integrating AI in Drone Navigation for Wind Turbine Inspection. It's a fancy title, I know, but we are actually doing a little bit of AI, but I will also present some of the other stuff we're doing that is not related to that. The content today will be a little short story about myself and what I'm actually doing. Then I'll talk a little bit about Aalborg University in general and our campus in Esbjerg, and also about Esbjerg and why Esbjerg is a specific city or special city for Denmark, and how that influences us at our campus. Probably most of you listening here have never heard about Esbjerg, but maybe somebody has. But I'll show you a little where we are and who we are. Then I'll discuss a little bit about the inspections of wind turbines and why we think that is important, and that will be kind of the motivation for all our research. And that's one of the things that we strive to do here at Aalborg University is link the research to real life applications, such that we can help the society as best we can, of course. Next, I will introduce our Quanser AVRS setup. You probably very well know what it consists of, but I'll just show you our lab. Our lab might be smaller than the usual lab, but that's what the space we had. And next, I will introduce some of our work that we have been working on drones with the Quanser system. I will not go into all the other stuff we are doing. We of course do a lot of things that are not related to indoors testing. We do some outdoors testing as well. I might mention a few things, but this is not the core topic of today. And then there will be a question session you can ask me, and I'll try and answer as good as I can. So shortly about myself, I was born in '86 in Yugoslavia, and in '92 or '91 we fled due to the civil war to Denmark, and actually I've been living in Denmark ever since. I grew up 30 kilometers away from this campus, so I'm kind of local here and feel very local as well. My current position is assistant professor at the Department of Energy Technology, Aalborg University in Esbjerg campus. So my education background is I got my bachelor's in engineering in electronics and computer engineering at Aalborg University, the same campus back in '11, and I continued after that with a master's in engineering in information and with specialization in intelligent reliable systems, which essentially is control systems reliability oriented study. And this was also at Aalborg University Esbjerg campus, and I finished in 2013 August. And my master thesis was modeling and control of distillation systems for ethanol distillation for use in cars, internal combustion engines, with a Danish energy company. And then my PhD, which was I finished in May 2017 with the title Real-Time Monitoring and Robust Control of Offshore De-oiling Processes, was also at Aalborg University. And just a little introduction to that is my supervisor is a local associate professor called Chen Yu Yang, who has been with the university since 91, I think. And that work was very different from robotics because most of my background is in process control, where we worked on control of de-oiling systems in the offshore environment. And just a little zoom in here. This what you see here is a separation system. So in the bottom, so if you follow my mouse, then down here we have some tanks with water and oil. We send this around the system all around our lab, and then we separate it up here in the gravity separation and the hydrocyclones. So I will not go into details here, but it's more to introduce that my work has originally been focused on processes. And I was actually, me and my colleague, we were actually the ones who also designed this setup. So we have tried a little bit of different things. So my research areas are modeling, control, instrumentation. We focus a lot on offshore oil and gas, but we are going away because funding is not easy to get in that dirty business anymore. So I've turned my focus towards onshore wastewater treatment systems for municipal wastewater treatment and mechatronic systems such as drones and robotics. And my main focus here is on control of the drones and navigation instrumentation of the drones. And that's the applications are mostly wind turbine inspections, and also we are trying to get into the wastewater pipeline inspections as well. At the university, I teach bachelor students currently in modeling and simulation and digital signal processing. I'll talk shortly about Aalborg University, but the way we work is that 50% of the time the students have classes and 50% is project work. So we have a huge supervision task where we have student groups working together on projects. So I supervise bachelor and master level students in robotics and process control. So currently we work on drone design, control and instrumentation, and on wastewater treatment onshore. So just shortly about where I kind of come from, the Aalborg University. This is actually is a picture a photograph actually I took today of our lobby just outside my office. We have this very fancy new building. That's good, one could say. Geographically speaking, we have 3 campuses. So the main Aalborg campus is up here in the north of Denmark, north of Jutland. This is the main peninsula called Jutland. Then we have the capital, Copenhagen. We have a campus over there on the Zealand island. And then Esbjerg campus is located here in the southern region of southern Denmark of Jutland. And you can see we are quite small campus with approximately 500 students divided between different departments. We have some chemistry, machine, civil engineering, and energy, or we mostly educate electronics engineers. And we have approximately 80 staff. So the entire university is rather not large. So we have different faculties where we are part of the engineering faculty with 3,800 students, 6 departments, almost 300 PhD students. So rather large department and almost 900 full-time employees. In total, it's a relatively large university for Denmark, but I know globally might be small. We have around 20,000 students and almost 3,000 part-time students and 900 PhD students. So for Denmark, which has 5 million people, this is a pretty large scale. Everything in Denmark is small, so for us this is relatively large. What I said earlier and why we also need the Quanser system, or not need, but we need something like the Quanser system, and we chose the Quanser system, is that we educate students using this problem and project-based learning, what we call PBL, and that means that the students 50% of their time is with projects and 50% of their time is with the courses. So they have a lot of project work that we need to kind of find some good projects that motivate them and make them, do their stuff and learn something. And that's why we also chose to invest in the Quanser system, because at that point it seemed very easy to go to. We didn't have to spend too much time on soldering and pulling wires ourselves. And just a little bit of bragging that we always told to do is that we actually were. There was a study based in MIT that put us as the 4th best university in the world, and we also known as Europe's best engineering program. So we are not nobody. We are pretty okay. So we are located in Esbjerg. This is our big monument called the Four White Men. Very interesting thing about Esbjerg is that it is actually the largest harbor on the Danish west coast. You can see here the harbor from the air. Down here you see a lot of oil and gas drill rigs, and over here you see wind turbine shipping harbor. And over here in the corner you see the world's largest wind turbines, the 8 megawatt wind turbines from Vestas, which is, as you probably know, Danish company. And in this corner here you see the university located over here. So it's a relatively small city with 70,000 people, but we have, as you can see, the industry is almost as large as the core of the city. It is actually Denmark's energy metropolis and seat of the oil and gas business. Also why my PhD work was on oil and gas, because we are so closely tied to them. And you can see here, this is the Denmark. Then you can see this area here is all our oil fields. So it's very convenient for us to work with that topic. But as oil is a dirty business, we try to get away from it, and we try to focus on wind turbines. And as you can see, Esbjerg is the main hub for export of the Danish production of wind turbines, both from Siemens Gamesa and from Vestas. And we have a large throughput of wind turbines. And that also means that we have a lot of companies working with wind turbines, and we try as a university to support them in the best ways we can, both in the design of wind turbines, but also in maintenance of wind turbines. And this picture I think is very interesting. Here's a large one. You can see the scope of the wind turbines in our harbor. And a very interesting thing about this image as well is that you see in the background here a coal-powered plant, which is now being converted to green energy. And you see the old oil rigs over here parked because the oil prices have forced them to be less in business. And then you see our large wind turbines here taking over. So we are proud of that. And I think Denmark in general is one of the leading countries in green energy. So that is what brings us to wind turbine inspections. So I will talk a little bit about the motivation. This picture we took while we were doing some preliminary study together with some local companies that do maintenance. So wind turbine inspections. So the number of installed wind turbines is constantly increasing. Back in 2016, there was 340,000 wind turbines globally, and that number is set to increase drastically. In Denmark, in 2018, actually we had 40.7% of the energy supply covered by wind energy. So we are becoming more and more reliant on this energy source. But there's also growing demand for periodic inspections of wind turbine, because we need to maintain these, as I will come back to soon. And this is currently predominantly done using manually by using specialized pilots. And this picture on the right is actually a pilot flying and taking images of wind turbine blade, which is laborious, and automation can definitely help you, not just to make the job faster, but also higher precision and remove the people from these dangerous areas. And it's also quite expensive because offshore we have to count in the prices of sailing. Another thing is that failures in wind turbines can be dangerous and expensive, and they're definitely not environmentally friendly. We spread residues of plastic and smoke everywhere. And you can see this picture actually is my own photo from Northern Jutland, a wind turbine that burned half a year ago. And then it's not pretty, but it also pollutes. So one of the things that we look at is that the prolongation of the wind turbines reduces their CO2 footprint. For example, 60 megawatts of wind turbines require 7.9 million kilos of materials, where the major part comes from ferrous metals, which accounts for around 6.5 million kilos, which are large numbers. And some studies show that lifetime emission intensity of a wind turbine ranges from 5 to 8 grams of CO2 per kilowatt. So that means we are not in zero, but we can get closer to zero if we prolong the life. So that means we have to build less wind turbines and let them run for a longer time. So that's our key motivation. Another thing is that some studies show that erosion of wind turbine blades, as you can see on this picture, that we took some with our partners doing some test of our hardware, have been shown to reduce the energy production by 5%. So by maintaining these wind turbines, we can increase the energy production. And another thing is that offshore drone inspections are very polluting. It takes roughly a ton of CO2 per wind turbine because of the vessel charter when sailing. And we see automation be able to decrease this inspection time and the use of vessels. And if going fully autonomous, no vessels will be required, as the drones will be out there doing the job by themselves. So our goal is to design a fully autonomous drone platform that can perform wind turbine inspections and also enhance the quality of the inspection material, so the images and data that is collected. Our first step was to look a little bit more at how do we navigate in these environments, and we started by looking at combining classical control and some vision based methods. So what we did was we looked at recognition of wind turbines visually, and then autonomously navigating without using GPS. So I'll shortly talk a little bit about our Quanser setup before I go to some of our work that we have done. So here you see an entrance to the lab, just so to give you a visual tour, and no eating, and only for instructed personnel, it says on the door. So inside of the lab, you see here our Quanser setup. We have the typical 3 screens here and the PC. We have 2 drones and 2 Q-bots. The Q-bots we mostly use for students to do path following and optimal path finding, and we are now looking at using them for teaching students about LiDAR and SLAM. And the drones we use also for teaching and for research. And our setup is set up in a quite traditional manner. You can see our cameras are set up in this aluminum profile. One of the issues that we had was that the profile was touched by certain constructions in the building, and that actually ruined our calibrations quite often. And also they have been changing our facade on the outside, so that has also been really irritating. So if you install this system in your lab, make sure that nobody touches it. Keep people away. That's my best recommendation. Yeah, this is just another angle. You can see the drones, the batteries, and the Q-bots. And the camera position, you can see we set them hang up, so we remove some of the vibrations from the construction. So I would like to start talking a little bit about some of the work we've done. I will not go into heavy detail on how we have done it. You can this first work that I'll show you is actually paper will be published soon. We have presented it in a conference, so it was presented in Poland at the 10th ISAC Symposium on Intelligent Autonomous Vehicles. And the paper is about visual aided navigation of a quadrotor for autonomous wind farm inspection. So this is the first kind of work we did with the Quanser setup, and also in general with robotics and visual navigation. So what we did was we implemented a DNN that was specifically trained to recognize wind turbines. And we adapted a well-known network called AlexNet and trained it using transfer learning with images that we had from the lab. So the picture you're seeing right here is actually a newer picture than what originally was done. Originally, we didn't have this beautiful little model here. We only had a picture of a wind turbine, as you will see in the video. And the reason why we used AlexNet also because it's efficient for inferencing, but it's not as accurate as some of the newer networks. But it actually proved to be quite efficient for what we were doing. So in this first work, we just wanted to, as a proof of concept, show that we can recognize something and actually tell the drone to kind of stop and then kind of have some kind of visual intelligence. Yeah, shortly about the architecture. I think I won't go too much into detail, but it is essentially the standard AlexNet, where we have changed the last 3 layers and updated with some new outputs. One is the windmill, and the other one is the environment. So that means we can recognize either the windmill or the environment, and we achieve some pretty high accuracy. But of course, we know that in real life, this might not always tell the whole story. The controller that we use for this initial work, we first used the Quanser controller because we wanted to get acquainted with the system, and it worked very well for us. And the structure looks like this. We use the OptiTrack cameras to find our position, absolute position in the room, and then we use the IMU for our attitude control. And then our trajectory generator is done based on our cameras and our neural network. The current version of our system actually uses LQR with the Kalman filtering, but this was not used in this early work. So the system, the way we implemented this was that we had the ground control station and the drone, OptiTrack, and the vision controller used for navigation control and IMU, and then we have the drone control and the Wi-Fi communication. And this is pretty standard for the AVRS system that probably all of you are familiar with. So the initial test performed on the Quanser lab setup, the drone was programmed to search visually for the wind turbine. In this case, it was just a poster. We didn't have better than that. To find it and fly towards it. So actually we were able to do that, and I will show you a little video here of that happening. So I might just go forward. You can see takeoff, and what the drone is set to do is set to scan. You can see the camera and the laser from one of the cameras. You can see it's blinking over here. The drone is rotating, and while it's rotating, it's sending its own video feed that you can see in this corner back to the ground control station, which is running a neural network and inferencing. And as soon as the probability reaches a certain threshold, we activate the stop event and then move towards the wind turbine. And as you can see, that is working very well. We have recognized the wind turbine, and now we are flying towards it. and at some point we will stop because we stop a certain distance and then land. So very simple little piece of work where we try to use this extreme capability of neural networks and image recognition. This work was done together with, just to introduce some of my colleagues who are part of this robotics group. So it is myself, my colleague Daniel Arroyo, colleague Xiaobao Li, and colleague Chenyu Yang, who was, if you remember, my PhD supervisor, who is working still very closely with me. Well, go forward. So current work, I will not show you the newest work, but I will show you the work that we actually have a paper accepted on. So we expanded on this idea with using the neural network, but now we wanted to use the neural network for servoing, visual servoing. So this paper has been accepted for presentation at the 15th European Workshop on Advanced Control and Diagnosis, ACD, in 2019 in Italy, in Bologna. It's still the same group working on it, and essentially the title is Visual Servoing Navigation in Sparsely Populated Environments. So our motivation behind this work was that we wanted to navigate in this offshore environment and find a wind turbine and navigate towards it and actually use vision for inspection. And most of the work that we found using visual inputs like cameras at that point was where there was a path, but it was quite difficult for us because we were looking at the blue sky and that was challenging. So we wanted to try something different. So what we did was that in order to be able to know if we should go left or right, in this case, and up and down, which still was not done for this paper, we needed to segment the image into pieces. And what we then did with the segmentation was that we used the different inputs to turn either left or right using some algorithms. So that means we take the image from the camera, we segment the image. The segmented image we process through a neural network that is trained to find the wind turbine, and then the probabilities are used to calculate the error of the drone's relative position to the wind turbine. So I will not go too much into detail with this because this work has not yet been presented, but I will show you the video. Otherwise, this work will be published soon. So in the way this system works is that the drone takes off by the operator, and after that, the drone does everything on its own. What it's doing here is that it's searching for the wind turbine. As soon as one of the segments sees the wind turbine, the drone stops. When the drone stops, it starts navigating towards the wind turbine using the visual input both for collision avoidance and for yaw movement. You can see here it's actually moving forward and controlling yaw based on visual input. So there's no operator at this point. This is purely based on the segmented visual input and neural network calculations. And here we were really grateful that we had the Quanser system that we could actually test this and run these neural networks. We we were using quite a lot of the resources from the GPU, but it works very well. And you can see that we reach in front of the wind turbine and then we land when we have reached certain threshold for that determines our collision avoidance algorithm. I have a video here which I filmed with my cell phone while this was happening, so you can see the feed from each segment. So it's one camera but segmented, and soon I will move it over, and then you can see the probabilities calculated for each segment that we then use for the computation of the direction. So if you wait a little bit, this is the view of the drone from where we are sitting. If we move over here, I'll pause it for a second. You can see the 4 different probabilities, and you can see that yellow and blue are high. That is because the drone is that will be the 2 segments that actually see the turbine, the one that is highest. Oh, and you can see this happening in real time. And down here you can see the drone in front of the wind turbine. So what has happened here is that this algorithm has been modified such that the drone does not stop. The collision avoidance makes the drone stop moving forward but does not land. So we just leave it here and let it continue servoing. And what we want to show is that we can continue servoing without the system going unstable here. Although we can't prove that the system is stable, we can statistically show after some time of experiment that the system continues to servo, and you can see the movement in yaw. This is due to the yaw controller moving forward, left and right, and this movement can be optimized by tuning the yaw controller, which is fed by the probabilities. We'll just let it play out. The video is slightly longer, but I have cut it here due to time issues. Come on. Yes. Another thing that we focused a lot on, since I focused a lot on control and my background, is design of control. So we have been looking at different control options. One of the things we did is something I did with some of my students. We designed an optimal controller, where we included the motor thrust dynamics as states, and evaluated the performance using the Quanser setup. And this is some of the data that we collected. You can see our blue reference simulation and our experiment. Performance, of course, it's not relative to anything here, but what I want to show is more how this AVRS system has been graceful to us and providing these extremely precise measurements from the OptiTrack system that we really like. But I will show you immediately the video where we are testing our controller to see how it works with disturbance inputs. So I go and give it a few flicks. So what we have here is 2 LQR controllers. One is designed for the position control, and the other one is for the attitude. And we use a Kalman filter to estimate our states. And we kind of internally joke that we have made a better controller than Quanser, so we hope we are right. The next thing I will show you is a project that we did together with a company. We call this the load stabilizing controller, but the idea is that we need to carry a load with the drone. And one of the reasons is for environmental photography. I will not go into details for what, because it's the company's right to share that knowledge. But what our task was to model this system. So to model the ball hanging underneath a drone. Here is one of our Matrice 600 Pro that I am flying to test the physics of the system, just to get an understanding. Inside of the ball, we had an accelerometer, gyroscope, magnetometer, so a full IMU system that we are recording the data to figure out how is the system actually performing, what are the dynamics, and so on. So we wanted to test this outside with a huge drone before putting it into our Quanser system. The next thing we did was that we developed a model. The model models the angle and rotation of the object relative to the drone, as you can see in this figure over here. So beta is the angle, and excuse me, and gamma here is the angle relative to the yaw of the body frame. The implementation that I will show you was initially done with a PID control. The video you are seeing is actually only a P controller, because we had some issues here, and we haven't continued. We haven't finished yet with that part, and we also were looking at MPC. But essentially, what we have is the inner outer loop, which is very similar to what you see in drone control. So we have the attitude controller and the position controller, and then the outer loop controller controls the position based on the error of the beta and the gamma. So these two angles of the ball, and the idea is that we want to stabilize the ball. We use the OptiTrack to track the drone and the load simultaneously. So at this point, we know the absolute position of both of them. So that, of course, helps us a lot in our achieving our goal. But let me show you the video without me talking too much. You can see here at the drone, there's a blue cord and the ball. It's a small ball that we 3D printed, which enable us to put IMUs inside. And you can see on it, we have the reflective balls. So what we do in this video is we fly from one side to the other to make it to make the ball start shaking, and then we turn on by a flip of a switch. We turn on the stabilizing control. So you can see the agitating movement. This is the agitating movement, and now we switch on the controller, and you can see the compensation by the drone, making it stop. The next what we did was that we take off and we fly in a circle. The white circle made by chalk on the floor is not representative of what we are flying. We use this to calibrate our camera, so don't focus on that. The drone will fly here in a counterclockwise direction, so it will disappear all of a sudden into the screen on the left side, and then it will reappear at the middle of the screen and come back to its natural position. So we are just flying here a model of a circle. So I should start now. So essentially, we have set the ball's position to be a circle, not the drone. The drone is just trying to maintain the ball's circle position. It's a bit difficult to see what's going on, but you can see it's not perfect. We had some issues with the weight of the ball. Depends on how light the ball is, because the turbulence from the propellers and sometimes is a quite dominant disturbance in the system. So that was my presentation for today. I think also I've used up my time. If you have any questions, please ask them. While you ask questions, I can quickly tell you before you start that here's a zoom in picture of our wind turbine storage area in our harbor, and you can see all of our wind turbine, offshore wind turbine installing vessels here, the rigs that they use. So enjoy the picture, and please, if you have some questions, now is the time.
Thank you, Petar, for that presentation. Some of the questions that we have here, I'll read them out. The first one is, what programming environment did you use for the deep neural network and AlexNet?
So because everything that your system provides is in MATLAB, we continued using MATLAB for that entire procedure.
So did that require any additional toolboxes?
Yes, so we used the image processing toolbox, the CUDA GPO coder toolbox, and TensorFlow, and you caught me there. I can't remember all the details.
That's perfect. That answers it, I hope. The other one was, how easy was it to interface with the hardware? did you have to develop code in Simulink from scratch, or were there examples to start with?
So for the initial work that you saw, we used the controller that you provided because we wanted to focus on this this crazy idea that we had that we could use this DNN to compute the the inputs to our attitude controller and position controller. Later on, we modified your code slightly, and then in the end, we started all over. But at that point, we have kind of learned the system, which was rather intuitive because we are used to using MATLAB and Simulink for teaching and research. And all the work since then here, I haven't shared all the work that we are working on. We kind of start from scratch now. So it is relatively easy because we are used to Simulink, I would say.
Okay, perfect. Thank you. The next one was, in the load balancing application example, did you have to track the position of the load? Did the load have an IMU in it? And was this necessary?
So we actually designed a small little IMU that we could communicate with the Quanser, the drone, using the IO. But for the experiments, we actually only use the abstract system because we wanted to know the absolute position. The next step is to use the onboard IMU that is inside of that little ball, and it's Inmasense. I think it's called 6050 IMU, which has an accelerometer and a magnetometer and a gyroscope. And the interface is done through serial communication with the drone, but the students were not too happy with doing everything in Simulink because we had to do a lot of conversions, the serial communication. So we actually I helped them put a microcontroller in between, so we actually can use the microcontroller as the kind of middle communication between the drone and the ball. So yeah.
Okay, perfect. Another question was, can you provide any more details on visual servoing and how you perform that?
So I would like the first work we did. I think it's better to look up the paper. But the second, I mean, I can also talk about the first one now. But the second one has not yet been published. It just accepted. We haven't presented it, so I will not go into too much detail because I actually don't know what you're supposed to do there. But the first one, I can tell you that what we did was that we just recognized the images, took the probability of seeing a wind turbine or not, and using that probability to trigger a switch that stops the visual the scanning and then starts moving in the one direction. It was pretty simple. The new part, we actually use multiple probabilities from all of the segments to compute the angle relative to the wind turbine based on the probability. But again, that I think that I will not talk too much about it because it is in the new paper and that has not yet been presented. So
yeah, that's definitely understandable. Another question was, did you test your work on real wind turbines?
So this exact what you have seen, we haven't because now going from the laboratory to the real environment, also something that I discussed with you guys is that there's of course a little step because we are going from one platform to another platform. So we are now working on Linux platforms where we want to implement something similar. Of course, we can't just export it directly, so we have to do some new work there. And I also discussed with you guys that in the future could be nice if there was maybe we could export directly to ROS or something like that.
Okay, yeah, we'll definitely take that into account. The next question was, Sorry?
Sorry. Yeah, I would just say that I have only showed the Quanser research that we do. We do a lot of direct cooperation with companies where we actually build software and hardware for the companies for inspection. We actually have some of our hardware and software right now flying in northern Sweden, helping with inspections that we have developed in-house, software and the hardware. And
Very cool.
that system is not used for navigation. It's actually used for enhanced data collection using equipment such as LiDAR and RTK.
Okay, sounds good. Another question was, how robust is the Q-drone platform to handle drops and damage?
So I have also, as you show, I can show a quick little video. Where is that? There it is. I have a little video of our many drops. So the platform itself is very robust. As you also know, in the initial testing there were a few issues, but I'm very happy to say that you helped us. I think we have sent the drone over to you guys, and you have updated some of the things that we damaged. But we have actually dropped them so many times, so we are very kind of satisfied with that part. We also careful, of course, to not give it to any student who will just go and step on it or whatever. So, but it can handle a lot of you saw that. Could you see that fall?
Yeah, we can see that fall.
Yeah, so we continued flying after that fall. There was no problem there. So we have crashed it a few times, and I think anybody who has worked with drones, if they haven't crashed the drone, I don't think they've been trying. So
that sounds good. Okay. Next question is, how did you find the position information of the identified wind turbine when doing the experiment with the Q-drone?
Sorry, say that again. I didn't catch the whole.
How did you find the position information of the identified wind turbine when doing the experiment with the Q-drone?
In the video I showed.
I guess, yes.
Yeah, so we don't know its position. We don't know its coordinates. So what we do is that based on what we see in the quadrants, we know is it relatively left or right to us based on the probability of us seeing it. So that's essentially what's going on, and we use that information to generate the error that we have, that our angle, so our yaw error, and then we kind of modify our angle and then fly towards it. And if we again deviate slightly, then we will move back again using this information. I hope that was answering it.
Yep, that I think does. There's another one that says, have you used any observer-based control methods?
So we have. So what we have now is the newest stuff we implemented is we have LQR controller implemented with where we actually have nonlinear Kalman filtering. It's quite standard configuration, but what we did was that we expanded the standard or the relatively standard drone model with the dynamic of the motor input. So we kind of add that in. Although we also tested, we have done extensive testing of the drone, and we figured out that I think I can't remember exactly the time constant, but it was around 50 milliseconds. So we are not really sure that actually information helps us much, but we have done it anyways.
Okay. The last question is, what is the maximum load your quadcopter can handle?
So the balls you saw we were flying with, while we were flying with them, we had the microcontroller on top. We had the large battery, not the one that was supplied, by you guys. We have bought some 4.4 amp batteries. So I think they were around 380 grams. So we have that battery, we have a microcontroller, and then we have a string with a ball, and the ball was with the IMU around 100 grams. And that actually worked very well because it's a dynamic load, so there was no problems there. Static load, we have had RP LiDAR, LiDARs from company RP LiDAR, the new model, the one that rotates, and that thing weighs I don't know, maybe 300-400 grams. You can I can't remember. You can check that information, but it's the, I'll just quickly double check so I don't say something wrong.
Yeah, that sounds consistent with what we expect as well. The Q drone, as it comes out of the box, can support up to 450 grams of a payload. Once you change the battery, you can add additional payload if desired as well.
Yeah. So the reason why we added extra batteries was not because of the payload. It was just because we wanted to run the RP LiDAR, which it uses some extra power. And then during testing, we just didn't want to change the batteries that often. But it's called the RP LiDAR A2. So if anybody is interested, you can check how much that weighs. I wouldn't recommend anybody using that too much because it's not a very good LiDAR, but it's good for students.
Okay, perfect. We have more questions actually. One says, what specific things are you hoping to use the drone to ultimately inspect?
So we have very close relations with one of the major Danish wind turbine inspectors, and they kind of give us many problems that we should help them with. But what normally is done is we want to design the drone so it can very reliably take images of cracks and estimate the size of the cracks. And we want not to see a crack which is 1 meter long and everything is actually going to hell. We want to know it when it's only a few centimeters long and maybe a few millimeters wide. So we want to be able to inspect almost anything. So,
okay, thank you.
That is.
Sorry, Petar, you want to continue?
Sorry?
You wanted to add something?
No, I also want to say that we aim at using the QBots for experiments with different methods for pipeline inspection, because we have done a lot of development in pipeline inspection. We have some of our own homemade pipeline robots. So we were also aiming at using this platform because we have it now as part of the system. But we don't know exactly what we are going to inspect. We just want to look at the control.
That's perfect. Yeah, we ourselves are adding support for Python right now to be able to access a lot of our devices. And in the near future, we'll have examples on how to do this as well. The Q drone itself directly has Python installed on it. So if you want to do additional development work, you can access it via terminal and do that as well. Yeah, thank you so much for answering all these questions, Petar.
Thanks, Petar, for your time and for the great presentation. And we are looking forward to our future collaboration with Aalborg University. Thank you, everyone, and have a great day.
You're welcome.